Hi everyone, this is Ms. Zarette here. In this video, I'm going to be walking you guys through section 7.7 in the textbook. Just like last time, you'll want a calculator to kind of help you get through some of these hefty calculations. So let's go ahead and get started. So remember that the original exponential formula is this. You've got some sort of initial value being multiplied with some sort of power, base b to the power x. When you're talking about exponential growth or decay, this b value, you're going to have to do a little work to get the b value. You're still going to have your initial value, but instead of just explicitly saying this is what the growth factor is, they're going to give you some sort of growth rate or decay rate, which we call our R value. And this is usually expressed as a percentage. If you're looking at an example that models exponential growth, you're going to add that R value with 1. This entire thing, in parentheses here, this 1 plus R, this entire thing is our B value, that growth factor. If it's exponential decay, you're going to take that that decay rate. In this case, it's not growth, it's decay. Again, expressed as a percent, and you're going to subtract it from 1 instead of adding it. This entire thing in parentheses is our b value when you're looking at that exponential function. And then x is the number of intervals, which is usually a time interval. It's not always time, but usually it is. So I know that it looks like there's a lot of complicated information on this slide. My suggestion, pause the video if you need to, make sure you have it all written down, and then just keep referencing these formulas and keep writing them. The more you write them, the more you use them, the easier it will be to remember them. And then maybe even make some index cards as you're learning different formulas and equations to help you memorize them. So let's take a look at an example. And based off the title, we should know that this is going to be a growth example, but if it didn't say this, here's what you would look for in the problem. It reads, since 2005, the amount of money spent at restaurants in the United States has increased by about 7% each year. So this keyword increased, that's how we know it's growth. If it's increasing, if the value is going up, then that is an exponential growth problem. In 2005, about $360 billion was spent at restaurants. If the trend continues, about how much will be spent at restaurants in 2015? Round to the nearest billion. So we are going to have to do a lot of rounding here. So when in doubt, start with what you know. For right now, that's just a formula. It's just an equation. And again, since I know it's growth based off of this word increased, I know I have to use this as my formula. A times the quantity 1 plus some sort of growth rate, all raised to the power x. And now that I know what formula to use, I can start going back into the problem and figuring out what's what. What does each variable represent? What's going to be each number? So the A value is your initial amount. In this particular example, we're looking at 2005 as like the starting point. So the initial amount is the number of, the amount of money that was spent in 2005, which we're told is 360 billion. Now, I'm going to do like they're doing in the word problem. I'm just going to write 360. And then when I do all my calculations, I'll tack on the word billion at the end. I'm not going to sit there and write all of those zeros. In fact, it's suggested that you don't do that because the bigger the number, your calculator's probably going to put it in scientific notation. We don't want that. We're just going to write 360, round at the end if we need to, and put the word billion on the end. The next variable I need to determine is my growth rate. And again, that's usually expressed as a percent. So my eyes are looking at this number because that's where the percent symbol is. That's my growth rate. And remember, it has to be expressed as a decimal. The easiest way to do that is to take the decimal point, which is understood to be on the end, and move it 2 places to the left. This is the same thing as dividing the number by 100. Just remember, if you use this shortcut method, there's an invisible 0 here. This changes this decimal this percent to 0.07. And the next thing that I need is the number of intervals that I have, which in this case are year intervals. Well, if my starting year was 2005 and we're ending at 2015, I need to calculate how many years has passed. I can do that by just subtracting. If I take the difference of the years, that's going to tell me that 10 years have passed. Now that I have values for all of my variables, it becomes a very plug and chug method. You plug the numbers in and you chug along with the calculator. You just use your calculator to make quick work of it. So it's going to be 1 plus r, so 1 plus this decimal, all raised to my interval, which is 10. And now I just use order of operations and my calculator to evaluate. I need to do what's in parentheses first. That's going to be quick and easy. I can do this part without a calculator. And now I can't do this part without a calculator. I need to evaluate this power before I multiply. Remember, exponents before you multiply, just in like it says in PEMDAS. Now when you do this, when you do 1.07 to the power 10, you're going to get a non-terminating decimal. What I'm going to do is I'm just going to leave that number on my calculator screen without clearing it. And to show my work, I'm just going to write down a few of those decimals here. 1.96715, and it just keeps going, right? But I'm not going to clear that number. I'm going to leave that number on my screen and then immediately take that answer and multiply it with the 360. And that's going to give me the following answer, 708 point, oops, did I make a mistake here? Let me just double check. 1.07 to the power 10, and then multiply that answer with 360. Okay, yeah, I agree with that. Okay, so this is what I'm getting, 708.1744, and it just keeps going again, right? And I'm going to round to the nearest billion. In other words, I'm going to round to the nearest integer. And that's going to be approximately 708 billion. And these were dollars. Okay, so the reason why I'm waiting to round at the end is so my answer is as accurate as possible. Maybe you rounded this number, right? Maybe you rounded to the hundredths place or the thousandths place. If you did that, we should still end up with a pretty similar answer. Okay, so if you're far off, then that means something else has gone wrong. So our answers might vary a teeny bit depending on how and when you're rounding. I suggest always waiting to round at the end, because then your answer will be as accurate as possible. Okay, so here's one for you to try. Okay, so I'm going to pause the video here, give this one a go, and then when you unpause, you'll see a solution. Okay, so here's what you should have gotten as an answer, more or less. You should have been in the ballpark at the very least, very, very close. It did say to round to the nearest integer, so this is what I ended up getting. Again, I'm waiting to round at the very end, so my answer is as accurate as possible. So I got 4,872 subscribers. So I'll kind of walk you through how I'm getting that. Again, I know that it's growth because in the problem, it's saying that the number of subscribers is increasing. So I want to use this formula. And then the starting value, which we're saying is in 1985, that was 285 cell phone subscribers. The growth rate is 75%. If I express it as a decimal, it's 0.75. And then we want to know how many subscribers were there in 1994. So I need to figure out what's my X value, what are my time intervals. So to figure out my time interval, I just subtract the years, and that's going to give me 9. There are 9 time intervals, 9 years. Once you have all of the numbers, you substitute and solve. I have to do what's in parentheses first, raise that decimal to the power 9, which is going to give you this non-terminating decimal. So again, I waited to round at the very end. I kept this decimal on my calculator screen, then multiplied with 285, kept this number on my screen, and then used that to round. I rounded to the nearest integer. So hopefully we matched on that. Now let's take a look at an example of where exponential growth is used, every single day in, our everyday lives. And that is compound interest. Compound interest is a real world example, a real life application of where exponential growth is used. Banks use them, specifically when a bank pays interest on both the interest and the principal for money that is in an account. When that happens, this is known as compound interest. So not only is it gaining interest on the amount of money that was put in, but any interest that amount of money has earned is also gaining more interest. So it's gaining interest on top of interest. So the compound interest formula is very similar to our exponential growth formula with a couple of differences. Instead of the A value, we call it the P value. It's the same thing. It's the starting amount. It's the initial deposit. In this particular case, instead of saying, y equals, we usually say A equals, but they kind of are interchangeable. Sometimes I write Y equals, but basically the answer that you get is the balance that you have at the end after your money has gained interest. The R value is the annual interest rate, again, usually given as a percent, but expressed as a decimal. N is the number of times that interest is compounded per year. And then T is the time in years. So for a lot of these problems, this value N is going to come from a word. It's not going to actually tell you the number. It'll usually say that the interest is compounded semi-annually or quarterly or monthly. So you have to be able to look at those words and translate it into a number. Okay, so let's take a look at some examples using compound interest. Suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest, compounded quarterly. What will the account balance be after 18 years? Okay, so again, if you don't know where to start, always start with writing an equation. Our compound interest equation is our account equals our starting principal times the quantity, 1 plus our annual rate divided by the number of times it's compounded in a year, all raised to that value N times T, which T is the number of years. So once I've got a formula down, I start replacing all of these variables with numbers. P is your starting amount. It's your initial deposit. These parents initially deposited $2,000. That's our P value. Our R value is our annual interest rate, which we're told is 4.5%. And again, we don't want to leave it as a percent. We want to express it as a decimal. I can either divide it by 100 or simply move my decimal 2 places to the left. Just make sure when you do that, that empty space gets a 0. Oops. Okay, and then my N value, that comes from this word. It's saying that it's compounded quarterly. Okay, quarterly translates into a number. When I think of the word quarterly, I think of quarters, like in money. How many quarters make a dollar? 4 quarters. So how many quarters make a year? 4 quarters. So quarterly means that our N value is 4. And then what will the account balance be after 18 years? This tells me that my T value is 18. Once we've got all the numbers, plug and chug. It's a rinse and repeat method. My account balance is going to be 2,000 times the quantity, 1 plus 0.05 divided by 4, all raised to the 4 times 18. Now, I'm just going to use order of operations to simplify. I have to do what's in parentheses first, and in parentheses, I've got two operations, addition and division. In math, we divide before we add. So if I do that, and I'm just going to use my calculator here, I get the decimal 0.01125. And I am writing the whole thing here because it does terminate. And I'm actually going to simplify this exponent in the same step because that's not going to affect my order of operations. So 4 times 18 gives me 72. And now I'm going to add in my parentheses. I'm going to add that decimal to the 1, which I can do that without a calculator. I just make that 0 a 1. And now I will use my calculator. I have to take care of this exponent first, which tells me, do this power and then multiply with 2,000 last. So 1.01125 to the power 72 is going to give me a non-terminating decimal. So again, I'm not going to clear that. I'm going to leave that on my screen. And I'm just going to write a few decimals on my paper. And it doesn't terminate, so I'm just going to, write a few. And then without clearing my screen, I'm going to take that decimal and then multiply that answer with 2,000. And that's going to give me the following. 4475.53016. It just keeps going. So you might be wondering, how do I know where to round? This problem didn't tell me. Well, think about it. This is money. How many decimal places do we usually write for money? 2 places. We round to the penny place. So for a compound interest problem, it's usually implied, unless otherwise stated, that we want to round to that hundredths place. So for this one, that's going to round to $4,475.53. Here's one for you to try. It's basically the same problem, but instead of compounded quarterly, it's compounded monthly. But it's still going to be the same starting principle, the same interest rate, the same number of years. The only thing that's changing is your end value. So go ahead and give this one a try. When you unpause, you'll see a solution. Okay, so hopefully you were able to reference the previous example and this one wasn't too difficult. So this is what you should have gotten, or at least super close to it, for your final answer. Again, I'm waiting to round at the very end. It's highly recommended that you do that as well. The only thing, like I said, that changed in this problem is your end value. Compounded monthly, so again, think about it. How many months in a year? 12 months. So our end value is going to be 12. So instead of dividing that number by 4 in the parentheses, you're going to divide by 12, which will change that decimal. Again, I wrote the whole thing because it terminated. It's not a short decimal, it's pretty long, but we want our answers to be accurate. And it also changes our exponent. Instead of 4 times 18, it's 12 times 18, which gives us an exponent of 216. And then just following order of operations, I got down to my final answer, and then that's when I rounded, and I got $4,489.01. Again, we're just rounding to that pennies place because that's typically where we write money. Let's take a look at another example here. And again, based off the title, you would know that this is going to be modeling exponential decay. But if it didn't say that, then you would use the key words and phrases to kind of help you figure that out. It says the kilopascal is the unit of measure for atmospheric pressure, and I hope I'm pronouncing that right. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter increase in altitude, the pressure decreases, okay, by about 11.5%. What is the approximate pressure at an altitude of 3,000 meters? Okay, so be very careful with this one. It's saying increase and then it's also saying decrease. You have to think about what it's asking you to solve for. It's asking us to solve for the approximate pressure. Well, when I read the problem, how does pressure change? Does pressure increase or is it telling me the pressure is going to decrease? Well, it's telling me the pressure is going to decrease as we keep increasing the altitude. So because the pressure is decreasing, I know that this has to be decay. So the formula that we want to use is y equals some initial value A times the quantity 1 minus our decay rate, not plus. When it's decay, we subtract, all raised to the exponent x. So now that I have my formula, I need to start figuring out what are the numbers that go in place of these variables. Well, the A value is your initial amount, and we're looking at the initial amount at sea level, okay? So at sea level, we're told that the pressure is 101 kilopascals. The next thing that we need is our decay rate, which is often expressed as a percent. We're told that the pressure decreases by 11.5%. And again, I want to actually change this to a decimal, and I can do that by moving my decimal point 2 places to the left, which is the same as dividing it by 100. And here's the hard part about this problem. We want to know what our increment difference is for x. However, you have to think about the problem a little bit more here. So just take a second and reread it. When we're at sea level, we're looking at that as if it's like an x value of 0, okay? So at sea level, our x value is 0. And then it's saying for every 1,000 meter increase, okay? So we need to think about how is this increment changing when we get to 3,000 meters, okay? So it's an increase of 1 increment when it increases by 1,000 meters. When we get to 2,000 meters, that's another 1,000 meter increase. So our increment would be 2. And then finally, at 3,000 meters, that's our third increment, okay? That's how many 1,000 meter increments there are above sea level, okay? It's not going to be 3,000 as our exponent. It's actually 3, because you have to think about what the increments are actually increasing by, okay? So we're not just going to subtract here 3,000 minus, 0 for our sea level to get 3,000. It's really 3. That's our increment. Okay, a little bit confusing on this problem. We did a problem last time in the last video where we looked at a problem for rabbits, and it gave you some number of years, but you had to look at the increments as half years. Kind of a similar idea here. Our increments are increasing by 1,000, so you have to think, you go from 0 to 1,000, 2,000, 3,000. How many increments is that? Well, 1, 2, 3. That's our third increment. That's why we're using that for our x. So I would say that's probably the hardest part. Can I just delete that? No, I'm just going to erase it. I'm just going to erase all of this to make more space. So I would say that's one of the hardest parts about this problem. You have to think a little more complex to get that x value. It's not 3,000. Once you have all of the numbers, same as before, it's a plug and chug method. I'm just going to substitute everything in. Just be careful, it's not a plus sign, it's a minus. So we're subtracting that decimal of 0.115, and our exponent again is 3. Now I can just follow order of operations, which says subtract in my parentheses, and I'm just going to use my calculator to make quick work of it. That gives me 0.885. Now I'm going to evaluate that power, and I'm going to write, a few decimal points, and I'm not going to clear it if it doesn't terminate. I'm going to round at the very end. So 0.885 to the power 3 gives me 0.693154, and it just keeps on going. Now, without clearing that decimal, I'm going to take that value and multiply it with 101, and I get 70.008, and it just keeps on going. And it says to round to the nearest kilopascal, in other words, round to the nearest whole number, which in this case would be 70 kilopascals. I have no idea how to abbreviate that, so I'm just going to write the word kilopascals. And that would be our final answer for that one. So again, from the previous problem, what is the atmospheric pressure at an altitude of 5,000 meters? So again, you have to think about how many 1,000 increments is that above sea level, which sea level, you're assuming that's, 0 meters. So go ahead, pause the video, give this one a try, and then when you unpause, you'll see a solution. Okay, so here's what you should have gotten as your answer. Everything was the same except for your interval here. At a altitude of 5,000 meters, again, you have to think about how many 1,000 meter intervals is that above sea level. So at sea level, you're at 0, and then you go 1,000, 2,000, 3,000, 4,000, and then finally 5,000. This is 1 increment, 2 increments, 3 increments, 4 increments, and 5 increments. So you should have just replaced that x value with 5 in this problem. So once you've got all of your numbers, you just do what's in parentheses first. That's going to be the same as the last problem because our decay rate's the same. Evaluate your power. This is what's going to change. And again, I rounded at the very end. So I'm just including a few of my decimals here, but I've left that answer in my calculator, multiplied it by 101, and got this. It says in the previous problem to round to the nearest kilopascal, so I did the same thing here and just rounded that to the nearest whole number. So this number here told me to round that 4 up to a 5. So you should have gotten somewhere in the ballpark of this, depending on when and how you were rounding. Again, it is always recommended to round at the very end, so our answer is as accurate as possible. So I got 55. And I believe that may have been the last example. It was. So I will end this video here. I hope that you found it helpful and not too confusing. Like I said, if need be, pause, rewind, make sure you're writing everything down, and just keep practicing. It does get easier. And I'll see you guys next time. Take care.